Well, welcome to your residency for the first years. And this talk, if there's second and third years on, I don't think I gave this to you guys last year. So this is a new talk. So if you want to learn about normal skin, that's what this talk is about. And I try to give it basically, I think normal skin talks can be kind of boring. And so I thought what I would do is basically, I tried to spice it up with some interesting sort of facts. So anyway, for those of you who didn't know, your skin is home to more than 1,000 species of bacteria. Interesting. Your skin renews itself every 28 to 45 days, depending on who you read, but generally about once a month, your skin turns itself over. In some diseases, like psoriasis, that's about every 2 days. So that's why your skin scales a whole lot when you deal with psoriasis. And then your skin comprises about 1 billion tons of dust in the Earth's atmosphere, dead skin. Interesting. Your average person's skin covers about 2 square meters. We always talk about skin being the largest organ. Indeed, it is. It accounts for about 15% of your body weight, which is interesting. You have about 21 square feet of skin, which weighs 9 pounds and is more than 11 miles of blood vessels, which is interesting too. And then you have about 300 million skin cells. And if you take a square inch, you have about 19 million cells and up to 300 sweat glands, depending on which part of the body you're on. So if you take a punch biopsy, for example, that's less than a square inch, but still you're probably sampling, 8 million cells when you do that. And when you do a little a biopsy, you're looking at just one slice of that. You're looking at a far, far fewer number of the number of cells that you're actually sampling. So let's talk about histology, normal skin, because in order to do dermatopathology, you have to know what's normal and then what's abnormal. So that's kind of the purpose of this talk. We're trying to keep it somewhat light and interesting for you. So the most common site of taking skin biopsies is the trunk or the extremity. This is just kind of generic skin. It doesn't have a lot of extra sort of things on here. You can see the epidermis, the papillodermis. There's a sebaceous gland in there and big thick reticular dermis. So that's kind of the area that we usually biopsy. This is sort of a diagram, if you will, of all the things that live in your skin. And, this kind of looks a little bit boring. You look at this, it's kind of interesting. I mean, it's got a lot of different structures in here, nerve-related structures, blood vessels, sweat glands, sebaceous glands, apocrine glands, et cetera. So it's actually a pretty interesting organ, if you will. So let's start off talking about the epidermis. And basically, the kind of purpose of the epidermis is to provide a barrier between your internal functioning part of your body and the external environment where there's all sorts of bad things that live out there. Viruses, bacteria, ultraviolet light, things of that nature. And the purpose of your epidermis really is to make a stratum corneum, which is really that barrier, if you will. People who don't have stratum corneum, their barrier function is diminished and they get exposed to allergens and things like that and develop irritant dermatitis and contact dermatitis more readily. So you really need that stratum corneum. Usually it's basket weave, but it's compact on volar skin. And some other things that live in the epidermis, most of them are keratinocytes, as you can see on the right there. All these are keratinocytes, but there are other cells that live there. Langerhans cells, melanocytes, Merkel cells, et cetera. We'll talk a little bit about some of those. So again, it is a stratified squamous epithelium. You probably remember from histology in medical school, there's a lot of different other kinds of epithelium. Ciliated epithelium, columnar epithelium, et cetera. But the skin, epidermis, is stratified squamous epithelium. Notice that here they say it renews itself every 45 days. So the other slide said 28 days, here it says 45 days. So depending on who you read, it's around about a month in general. 90% of the cells in the epidermis are keratinocytes, and their goal is to produce keratin. And basically in areas where the skin gets really thick, it's a much thicker cornified layer, and if you keep rubbing it, it actually can form calluses, and we see that with lichen simplex chronicus. It also produces hair and nails. Other cells that live in the epidermis, melanocytes, you can see that diagram there on the left. Melanocytes are dendritic. They have these little dendritic processes that extend between the keratinocytes, and they actually inject their melanin into the keratinocytes. And then the melanin kind of migrates to the top of the keratinocyte. So that's basically what produces pigment in your skin. And when you get a tan or your skin becomes tan, well, you get more of those melanin granules that get formed in an attempt to prevent further DNA mutation from UV damage. So really and truly, there is no such thing as a safe tan. Well, you hear that, but that's your body is saying, wait a minute, I've been damaged by the sun, and you produce some more melanin to prevent further damage. That's kind of what's happening biologically. The reason that your keratinocytes stay very close to one another is because they have these desmosomes. These are tight junctions. They basically glue the keratinocytes together. And the hemidesmosomes are present on the basal cells, and they kind of anchor the basal cells to the basal membrane. And you'll learn a lot about that basal membrane over the course of your 3 years in residency. A lot of diseases affect the basal membrane zone. There are things that other antibodies target, things like bullous pemphigoid antigen. You can get loss of anchoring fibrils and some of the conditions like epidermolysis bullosa. So you'll learn a lot about this as time goes on. This is a nice example to show those hemidesmosomes and desmosomes kind of holding the keratinocytes together and to that basal membrane zone there. So the 5 layers of the epidermis, we don't really use these Latin terms all that much anymore. Stratum corneum, yes, but hardly anybody talks about, stratum granulosum or spinosum or basal. We just talk about the basal cell, the granular cell layer. So we generally translate this into English. But if you want to know these, this is a little mnemonic device that they didn't know how to spell properly, whoever did this slide. Come, let's get sunburn. Well, let's hope we don't do that. But if you go on TikTok today and listen to some of those imbeciles that are saying that they don't use sunscreens and go out in the sun and get lots of sun, maybe they want to use that mnemonic device. They're going to create a lot more business for us as time goes on. Stratum corneum, outermost 50 to 30 layers of cells. You can see that guy pulling a little piece of that skin up there. That's the normal stratum corneum. That's just it looks thin, but it's actually got about 30 layers of cells in there. And again, this is a waterproof structure. And this is something this is the purpose of your epidermis, really. It's producing this, just like it produces claws and hair. It's producing the stratum corneum to produce a protective barrier for you. And that's the purpose of it. And so these, again, will kind of stay on about a couple of weeks before they slough off. They're very dry. The bacteria can't get in there. They contain things like cathelicidins and other stuff like that are sort of almost like, they're not really immune related protective structures. They're more almost kind of like chemical protective structures that are antibacterial also. So your stratum corneum really keeps your skin safe and from your body getting infected and whatnot by a lot of exogenous things in the atmosphere. Stratum lucidum, this is seen beneath the stratum corneum, and really you don't see this on routine biopsies unless you're biopsying something like a palm or sole. So it's that little clear area that's just beneath that stratum corneum. You see that on the left there. If you rub your skin and it gets really, really thick, it can develop a stratum lucidum also, but it's usually seen on volar skin. Granular cell layer, basically that's where you get these carohyaline granules that are present in the very uppermost part of the epidermis. They're the cell, as you go from the basal cell layer to the top, the carohyaline granules, they're actually the beginning to form the keratin, and so they look purplish on H&E because they're acidic, and then they eventually form the stratum corneum. So that's kind of how that works. The spinous cell layer, it's called that because you can see a lot of desmosomes in that area. So if you're looking at it on routine microscopy, you see a lot of desmosomes, and they look like little spines, and that's where the keratinocytes are kind of held together. And they actually do contain Langerhans cells in that area. And then the basal cell layer, this is the germinative cell layer of your skin. So basically the stem cells live here, and these are the cells that are rapidly migrating and they're undergoing mitosis. So these are the cells that are forming the cells as they go they're mitotically active, and then it becomes less mitotically active as you go to the very surface. So if you see somebody with psoriasis, for example, we talk about suprabasilar mitoses. Normally the basal cells where the mitotic figures occur, but if you get up and you see mitoses sitting up there in the granular cell layer or just beneath that, and we say, gosh, that's a sign of rapid turnover. It's often seen in psoriasis. And there are also other cells that live here. The melanocytes live here. Merkel cells that are related to tactile sensation, they live here. Nerves will intercalate with some of these cells, so that's actually how you can feel things. And then the epidermal rete here, these are the things that actually form your fingerprints. And this is obviously it's basically it's almost like a fractal. I mean, these things are random. And that's why everybody's fingerprints really look different. Okay, so moving from the epidermis into the papillary dermis, this is the structure just beneath the epidermis, and it is a loose connective tissue structure. So you compare the picture here, the stratum, you see the epidermis, then you see the papillary dermis, and then you see the reticular dermis. The reticular dermis is comprised of a different type of collagen than the papillary dermis. The papillary dermis is a loose type of connective tissue, and it's expansile. You can get striking edema of the papillary dermis. It can really look like the lesion is becoming vesicular, but it isn't really vesicular. It's just because the papillary dermis becomes very edematous. And it can be very expansile also. You can get neoplasms like melanoma can fill the papillary dermis and expand it before they enter the reticular dermis. So it's interesting, and it's homologous with the periadnexal stroma surrounding follicles and eccrine structures. So these are little finger-like projections. You can see them over here. And because they form these digitations that intercalate with the epidermal rete, this is what forms really a very strong tensile strength in your skin. So in other words, if you don't really have any epidermal rete, and as people get older, they don't have as many epidermal rete or papillary dermal papillae, and so their skin is looser and it can be torn a lot easier. And some parts of the body, for example, like on your palms and so, you got lots of epidermal rete. That skin has to be really, really very, very thick and firm, and it's got to be able to do things like open doors and open, bottles and jars and things like that. So you kind of need that skin to be firm, and because it's interfacing with the outside world more than, say, your skin maybe on your back or your eyelid, for example, where that skin is very, very thin and needs to be able to move a lot when you blink, obviously. So depending on where you are, you have more of those dermal papillae and epidermal rete ridges. So if you look at that papillary dermis on high magnification, you can see it's got this very loose, areolar-like connective tissue, reticular fibers, collagen fibers, a lot of elastic fibers, some inflammatory cells, mast cells live in that area. So it's a looser stroma than you see in the reticular dermis. So this reticular dermis, and it looks sort of bland. It's comprised of thicker, ropier collagen bundles, usually type 1 and 3 collagen. This is the material that when you go into the tanning chemical reaction for leather, this is what forms shoe leather, basically. And so it's a very thick, very firm structure that actually protects your body from more mechanical trauma and things of that nature. But there are things that live in there. Blood vessels course through here. There are lymphatics. There are inflammatory cells that live in here. It actually can absorb a lot of fluid, so you can get edema of the reticular dermis, but it's hard to appreciate that when you look at it under the microscope. So you can see papillary dermal edema, it gets pale and light, but if you get edema of the reticular dermis, it's really not easily perceptible because it's just it kind of seeps between these thick collagen bundles in here, and there's such a large surface area available to it, you don't really appreciate it with histology. You can see these collagen bundles are much thicker. So it's not that loose areolar-like tissue with the papillary dermis. This is a thicker, ropier type of collagen here. Other cells that kind of live in this world, fibroblasts. These are the cells that produce the connective tissue. They produce collagen, elastin, reticular fibers. They produce hyaluronic acid. So again, your fibroblasts are critical because they produce all this collagen of your dermis. If you don't have fibroblasts, obviously you don't have any dermis. So if you have a condition like aplasia cutis, you don't have any dermis that's present there because you don't have any fibroblasts that are producing any collagen there. So if you just look at this chart, this kind of compares the papillary to the reticular dermis. Again, you can read this on your own, but basically think of the papillodermis as a loose structure that can be expansile, and the reticulodermis is a very thick, more rigid structure that provides a lot more tensile strength to your skin. Neurovascular bundles. These are seen mostly in the reticular dermis. We have blood vessels and nerve twigs that are surrounded by loose stroma. And so this is where we get inflammatory cells that localize when we're looking at inflammatory skin disease. We're talking about perivascular inflammation. Well, these are the little areas that those blood vessels are sort of targeted. The inflammation, the lymphocytes, for example, course through these small blood vessels and go around the blood vessels over here. So we talk about perivascular inflammation. That's kind of how it gets there. Nerves, a lot of nerves in your skin. You get lots of sensation. I mean, your skin is the source of sensation to the things that hit your skin, like heat, light touch, firm touch, pressure. Obviously, those things go to your skin first, and then they go to these little nerve endings, these little structures like free nerve endings, Krauss-end bulbs, Pacini corpuscles for pressure, et cetera. And then they go down these axons and end up in your spinal cord and up to your brain, et cetera. So obviously, your skin is super important for determining, neural sensation that we come into contact with. So you don't see a lot of these on routine histology, but basically they're important to know about. Adnexal structures, these are glands that live in our skin. There's not a lot of them, but there's about 4 or 5 that you really have to know about. Sebaceous glands, like you see here. We have eccrine sweat glands, and then we have apocrine glands. Your skin has about 2 million sebaceous glands. These are located kind of in specific areas of the body, like the face, for example, scalp. They have a peripheral germinative area. These are kind of analogous to your basal cells in your epidermis. And so these are the cells that are rapidly turning over, producing the sebaceous cells. And these sebaceous cells have lipid in their cytoplasm. That's why they kind of look clear at low magnification. And they produce their secretion by holocrine secretion. Is that it on here? Yeah. Okay, good. Holocrine secretion. We talk about holocrine secretion. You can think of that. The whole cell dies. All of its contents get dumped into the secretions. That's kind of a way to think about that. I'm not sure that's the exact origin of that term, but you can think about it that way. And this basically empties into the isthmus, right beneath the infundibulum of the hair follicle right here. That's where these sebaceous glands, their ducts, enter into the follicle at that site. And that actually arrives from this little zone called the mantle zone of the hair follicle. So here you see the sebum here. That's the secretion of the sebaceous gland. And these germinative cells form the mature cells. These mature cells just say, okay, we're ready to secrete our contents, and they just dump it all in here. And then it goes into the sebaceous duct and into your hair follicle here. And that keeps your hair is a little bit greasy. It actually moisturizes your hair follicle, and then it also actually moisturizes your skin. And so you put a little bit of sebum on there in your skin, coupled with your keratinocytes, you get a nice luxuriant structure there on your skin that feels nice and smooth. You have that. If it gets too greasy, obviously, people don't like that, but you need a little bit of this sebum on your skin to help with absorption of excess water and produce kind of waterproofs your skin a little bit. Apocrine glands are present in just specific areas of the body also, groin, axilla. They have these larger lumen than eccrine sweat glands we'll talk about in a minute. And they have this very characteristic type of secretion. We call it apocrine decapitation secretion. And what's happening there is, instead of the entire contents of the cell getting dumped into the duct, you have just the very tip of these cells kind of getting bitten off, if you will. And that's what forms the secretion here. So we call it decapitation secretion. Now, this apocrine sweat is odorless for the most part. There are sometimes it can have a little bit of odor to it as certain things get secreted into the sweat, but generally the sweat doesn't have any odor. But when it gets into your skin and then bacteria come in and act on it, it ferments it, and then it causes the production of chemicals that smell bad to us. And so that's why you actually develop body odor and things like that. So that's basically why your sweat smells bad. It's not the sweat itself, it's the byproducts of it being fermented. And apricot sweat has got more protein in it than eccrine sweat does. And eccrine sweat glands are present just about anywhere else on your body except your mucous membrane. So you don't see them on places like in your mouth, and genital areas, glans penis, for example, labia. You don't see it there, but you see it just about everywhere else. And the two structures, there's a glandular component, and then there's a ductal component. I'll show you a picture of that in a second. And the eccrine sweat gland, as opposed to apocrine sweat gland, is controlled by cholinergic innervation. So basically what happens is your sweat is produced almost analogous to the way that your urine is produced in the kidney. It just gets basically, when it goes into the sweat gland, it's basically isotonic. So it just kind of flows in there from your the little blood vessels here that are right around the sweat gland. So it gets in there. And then these white cells here that contain glycogen are ATP dependent cells that actually undergo a active reabsorption of the ions that are inside that sweat that gets produced there. So that sweat actually, as it goes from here up to the surface, is hypotonic. So if you actually go in here with a little, pipette and take out some of this sweat here, you can actually see, well, it has fewer ions than your serum has. However, when it gets to the top and then it evaporates, those ions that are there concentrate and it tastes salty to you. But the sweat itself is actually hypotonic. So just remember that. And if something happens and this cholinergic innervation gets disrupted by, say, a drug that patient may be taking, for example, they can lose fluid and electrolytes. So it can be a problem if you don't actually reabsorb those ions. And there are certain chemicals and drugs that get secreted in sweat. So here's the sweat duct as it's going up from the sweat gland down here to the surface, and it gets coiled in here, and then that sweat gets secreted and dumped up way up here in your stratum corneum. So comparing these eccrine, apocrine sweat glands, again, these are present just about everywhere. These are present just only in certain parts of the body. Sweat is odorless in both situations. This sweat doesn't really actually get decomposed by bacteria. That sweat itself, it's basically like water. So that it doesn't have any protein in it, as opposed to apocrine sweat. But when this sweat kind of interacts and gets into the stratum corneum, that gets wet and macerated, the bacteria can act on the sweat in the stratum corneum, the proteins of your stratum corneum, and that's what ferments with eccrine sweat. So that's why your feet smell bad and your sweat socks, when you don't wash them, they smell bad. It's because of the fermented stratum corneum, as opposed to apocrine sweat, which actually does ferment because it has bacteria, has protein in it that it can act upon. Hair follicles, you have about 100,000 of these normally on your scalp. There are really four major parts. There's the infundibulum, which basically means funnel. That's the upper part. It's got stratified squamous epithelium here. Then there's this mantle zone area. That's where the stem cells are, the bulge of the follicle. They live in that area. And then you get the isthmus, and then the inferior portion, which is the hair bulb and the cells that are rapidly producing. And this is what produces your hair shaft in here. And so this area here actually undergoes cycling. So this will live for a while, then it dies, and it kind of goes, these cells sort of degenerate and go up here. You get a little tiny bud here, and then it reforms another new inferior portion of the follicles. That's what happens when your hair undergoes the anagen, catagen, telogen cycle. So here's the inferior portion of the hair follicle, that nice little hair bulb, and these hair cells here, these matrical cells, these are the second fastest reproducing cells in your body. The number one structure is bone marrow, and the number two is the hair bulb, the papillae of your hair bulb. And so that's why when people get chemotherapy for cancers and whatnot, these cells that are rapidly proliferating die, and these hairs get shed. And that's why your bone marrow shuts down too, because those rapidly producing cells get killed. Cells that aren't rapidly producing don't get killed. They live and don't have any problems. So it's these cells that die when you get something that causes cells that are mitotically active to die. And then you can see some of the different linings of the hair follicle. We'll learn about those as time goes on. But you see the inner root sheath, the outer root sheath. It's got that clear glycogenated area, the cuticle of the outer root sheath over here. And here you see it in cross section. So here's the hair shaft, the cuticle of the inner root sheath, and the inner root sheath, and the outer root sheath, and the cuticle of the outer root sheath. So those are the structures of the hair itself. Beautiful. These are keratohyalin granules also. So instead of forming stratum corneum, these keratohyalin granules are forming a hair shaft. Okay, some fun facts about your hair. In 1950, only 5% of women dyed their hair. Now that is 75%. So things have changed a lot since that time. Cutting your hair, shaving it, doesn't make your hair grow any thicker or faster. People think it does, but it doesn't. It makes it feel maybe stubbly, but it doesn't actually change its growth phase. Again, the same keratin that makes your hair shaft makes claws and horns and feathers. One hair has a lifespan of about 5 years on your scalp and other parts of the body. Varies with certain diseases. Hair can grow anywhere in your body except palms and soles, your eyelids, lips, mucous membranes, etc. So if we see very thick cornified layer that looks like palm and sole, and there's a hair follicle there, you know that it has to have been rubbed. The most common hair color in the world is black, with red being the least common. Only 1% of people in the world have red hair. The only thing that can't be identified by your hair is gender. And interesting. Hair grows slightly faster in warm weather because it stimulates your circulation. 80% of Americans wash their hair twice a day. That is surprising to me. I didn't realize that. And then anticipation of sex makes your hair grow faster. I don't know about that either. I guess I didn't realize that until I did this lecture for you guys. This talks about hair loss, and as we get older, men and women, we both lose our hair. 70% of men by the age of 80 have lost over 70% of their hair. So that's what happens. And then same thing with women, they lose hair also. So again, female pattern hair loss, about 50% of women will lose some hair as time goes on. All right, subcutaneous fat, hot topic today with the new drugs like Ozempic and Mounjaro and whatnot. Again, we used to just think of fat as just being something that we didn't like it, and we wish we didn't have as much of it, but it's actually got a lot of important structures and important functions. So it does serve as a protective structure for you, but it's also a very hormonally active structure we know today. And it also contains a lot of blood vessels, nerves, et cetera, course through the fat. So it's an important, very important structure. There are really two main types of fat cells. There's the white fat cells and then the brown fat cells. We talked about the beige, the dipsites, but those really are kind of transitional cells. But these are present in infants. They have a lot of brown fat. They have a lot of mitochondria. They generate heat very quickly. There's usually very limited amount of this fat as we get older. When we're kids, our surface area is much greater. It's exposed to the body. So the amount of skin versus your internal organs when you're an infant is about 50-50. When you're an adult, it's about 70-30. You have a lot more skin as you get older compared to your internal organs. So your skin is way protective of your body as you get older, as opposed to when you're a little kid. So you can lose your temperature can change. You lose your heat pretty quickly and get hypothermic. That's why kids have to be in those little bassinets, and you keep them with blankets and whatnot when they're in the nursery, because they can lose temperature pretty quickly. So that's why they have this brown fat. If they get cold, they can generate fat very quickly. As we're adults, we have plenty of this white adipose tissue that protects us, and it stores energy and insulates us and keeps us warm. So we don't have to worry about freezing to death as much when we're older. Now, we've talked about just the general anatomy of the skin right there. What's interesting is there's a lot of regional variability depending on what part of the body you're on with what your skin looks like. So, for example, your scalp's got a lot of deeply rooted follicles. Your face has a lot of sebaceous glands. Eyelids very thin. And we'll ask you when we're looking at pathology, what part of the body do you think the biopsy was taken from? Because certain diseases affect certain parts of the body more frequently than others. You wouldn't diagnose somebody with dyshidrotic dermatitis, for example, on their back. So we say, well, if you can see a spongitic dermatitis on volar skin, well, that's more likely to be dyshidrotic dermatitis, say, than something like nubular dermatitis. So it's helpful. So here's your scalp. Normally we have 8 to 10 of these deeply rooted anagen follicles in a horizontal section like this. Your face, lots and lots of sebaceous lobules there. Eyelid, so this is a cross section of your entire eyelid here. Look how thin the epidermis is here, and it's got the skeletal muscle in here for blinking. It's got the little tear ducts down in here, and this is the mucosal surface of your eyelid. And that skin is super, super thin in your eyelid. This is just the skin of your back. This is where you take most of your biopsies from the trunk or extremity. Your leg, this is the lower leg, it's got these markedly thickened capillaries that are increased in number. That's normal, and that's just because of what happens when you stand. These capillaries have to be thicker. They're kind of supporting hydrostatic pressure because of your standing and walking all the time. You don't really have that over here in your back and other parts of the body because you're not really supporting a column of blood. This is volar skin, palm or sole, stratum lucidum up here. And then this is another higher magnification of that. And this is an erectile structure with a lot of smooth muscle bundles in here. This is the areola. This is a mucosal surface, lip. And here you've got a minor salivary gland. And notice the epidermis here doesn't have a stratum corneum. Very characteristic of mucosal epithelium. And it's also very clear and has a lot of glycogen within it. So that's mucosal epithelium. These are some of the cells that are in your skin. You can have inflammatory cells, non-inflammatory cells. We've already talked about some of those. Lymphocytes. Most of these are going to be T cells when you get an inflammatory skin disease. Sometimes you'll get some B cells, but usually they're T cells. When you look at these at low magnification, they really look black. They're very, very dark purple. They contain almost 100% DNA, which is obviously an acidic thing that when you stain it with the blue dye, the hematoxylin, it takes that up. Histiocytes, they look very pale at low magnification. Granulomatous inflammation, CD68 positive with that. Plasma cells have this very nice little characteristic clock face nucleus we talk about. And they also have this little perinuclear halo, which is where the immunoglobulins are located. Eosinophils in allergic reactions, things like bullous pemphigoid, for example, and they contain these eosinophilic red granules, that you can see here. And then neutrophils have the little convoluted nuclei here, very characteristic, no eosinophilic granules there. We sometimes will use myeloperoxidase to stain these. These are some red cells in contrast to the neutrophils. And then mast cells, these have little central nuclei with these little small granules in the cytoplasm. And if you look at them cut in cross section, they look like fried eggs like this. And if you look at them in longitudinal section, they kind of look like hot dogs. So that's a way you can kind of identify those. And they will stain positively with Wright stain, Giemsa stain, or with a CD117. They contain heparin and tryptase and histamine within them. And this is an example of that Wright stain. These are the mast cell granules there. Langerhans cells, these have these kind of kidney bean shaped nuclei. And they contain Burbeck granules, like little tennis rackets. And they stain positive for S100 protein and CD1A. And you don't usually see these in just regular routine H&E biopsies. You really have to stain these to see them. Usually we see them in things like Langerhans cell histiocytosis and in certain conditions. Okay, time for a quiz. See how much you remembered here. So how much of the world's dust is comprised of dead skin cells? You can answer silently. You don't have to scream it out here. 1 billion tons. It's a lot. So there's an old saying that given Avogadro's number of, if you have a mole of something, that's Avogadro's number of atoms are in it apparently, or molecules. There's about a 98.2% chance that the last one of the molecules in your lungs that you inhale came from Caesar's last breath. There's a statement that says that. So that's actually probably true, even though it happened a long time ago. That's how closely we probably interacted with one another. Average turnover of time of normal skin. This is one I hope you did remember. 6 weeks to a month, so depending on who you read. And the psoriasis, again, this is only 2 days, so very, very rapid. Where on your body is the skin the thickest and the thinnest? Your volar skin is the thickest and your eyelid skin is the thinnest. What kind of lymphocytes are present in most inflammatory skin diseases? Remember that too, T cells. And then what cell becomes malignant in melanoma? For all you know that, melanocyte.